So, good morning, everybody. I think we can start. There are people online, and I think who was going to connect has connected. So, first of all, yes, again, good morning. I'm very glad to introduce Domenico Trotta for this very interesting seminar on jumping out of the thermal bath and interplanetary shock in solar cycle 25. So just a few words to introduce Domenico. Domenico is very young. He has completed his PhD in 2019. He developed his activity at the Queen Mary University of London under the supervision of David Birch. And he has dedicated his research since then, I think, to the study of particle acceleration, both with simulation and observations, in situ observation in particular. Then he have a postdoc, and he was indeed leading our package for H 2020 project that was focused on the use of in situ observation for studying particle energy generation. And now he is in ESAC, and yes, he's using observation again to study shocks. He's using in particular solar orbiter observations, and he also is collaborating with Plasma Observatory because he's co-leading one of the working group that is taking care of simulation in support of the mission study. So please, Domenico, thank you very much.
Thank you very much for this very nice introduction. And yeah, I wanted to thank Federico, of course. Many people contributed to this material that I'm going to show today, so I want to thank them as well. And also I want to thank Oreste Pezzi. I mean, today is a seminar day, but this is part of a larger visit. We are collaborating. We are doing a couple of interesting, at least in my opinion, papers. And today, basically, we take a step back from these activities, which are somewhat focused. And I try to look at the big picture because I know that this is such a broad audience. I decided that for such a broad audience, I would go for a very cryptic title, Jumping Out of the Thermal Bath at Interplanetary Shocks in Solar Cycle 25. What I want to say is that I'm going to focus on a particular problem. That's the first stages of particle acceleration in a theoretical system. I'm going to do it at interplanetary shocks. We'll see in a moment why. And then I'm going to do it now, so in the solar cycle 25. This is due to the fact that the sun, our star, is very active, and it follows an 11-year cycle. So now we are at maximum. That's the, okay, there's a bit of a lag. Okay, so that's the outline of my talk then. I'm going to have a brief intro on shocks and shock acceleration so that we are all on the same page. Then I'm going to bring in interplanetary shocks and why are they interesting. Then I'm going to discuss about solar orbiter, as Federica mentioned, and a few friends. I'll try to convince you that we are living fundamentally a new golden era for space investigation because we have many vantage points in the solar system to observe things. And also these vantage points are very good. They bring new instrumentation and they make discoveries. I'm going to use solar orbiter and these friends to look at how shocks evolve and how proton accelerate. And then since there are a few astrophysicists, I'll make a case for electron acceleration in the heliosphere. That may be of interest to some of the community who look at emission, basically. So typically in the space science talk, somebody goes like, how about electrons? That's a typical question. So I try to go like this. On the right-hand side, you have basically the main course of the menu, solar eruptions. That is an image taken by a few telescopes of the sun. You see that the sun is active, it's gonna erupt, it's gonna drive material at very high speed. This material is gonna drive shock waves, which are my interest. You notice another thing, you see these white dots. These are not noise, these are high energy particle impact. So we learned that just with this video that the sun drives waves that are very high speed, they can perhaps accelerate particles. Also, I'm cheating a bit because it is the only remote sensing plot I'm going to show today. What we are going to look at, underwhelming, are going to be time series. So now And this is where the solar system or the heliosphere is really a special astrophysical system, you know? I can put a probe there and I can measure the local properties. So this is what a shock looks like for us today. This is a bit outdated, well, no, not outdated, but kind of legacy observations. You sit somewhere in the heliosphere and you have plasma going through. You see that when the event or the eruption comes, density goes up, speed goes up. This is the magnetic field, it goes up as well. And this is important. This is the flux of energetic particles. You see that there is an exponential rise up to the shock. So the shock is somewhere here. This is really the smoking gun that this system is accelerating particles in that moment in situ. So that gives a lot of information about the mechanism by which you accelerate particles, which hopefully are going to be universal and we can port to other systems. Importantly, though, I mean, we say this, we keep saying this, but there is also a loss of information because we moved from a video in which I see a large-scale eruption to a point in space and time. So that means that we have to shift a bit the way we think about this. Okay. So now with that knowledge, we define shocks. They are basically everywhere in the universe. The basic functioning is that they convert directed flow energy upstream into heat, magnetic energy downstream, and when collisions between particles are negligible, they can produce energetic particles. So this is a few examples of shocks. We start from the mantis shrimp, amazing animal, is punching supersonically, creating a shock somewhere there in the claw, up to our solar system in the middle. This is a lab shock on the left, but yeah, our solar system in the middle. We have CME shocks, so these are the progenitors of the shock we're going to study today. These are solar eruption driving very young and fast shocks. And also we have astrophysical systems where we can only probe these systems remotely. So spectacular emission from supernova remnants. And bottom right, you have the very large scale counterparts of the shock. That's a so-called radio relic. Is a megaparsec scale structure, and this is happening at the interface between two clusters of galaxies that are colliding. Our domestic or the closest shock we have is the Earth's bow shock, which is the result of the interaction between the supersonic solar wind. So sun is ejecting material all the time, which is supersonic, and the Earth to us is an obstacle. So at this interface, there must be a shock. I'm going to show a simulation of this shock because it's pretty much invisible, you know? We can't really do a picture of it, but we can do simulation and in situ investigation. So the shock is this paraboloid that you see, and you notice that there is a few interesting things. In particular, this system is developing a set of waves upstream. We call it the forest shock. It is basically this is plasma physics at its finest in a way. This is the shock propagating information upstream, even though the whole system is supersonic and it shouldn't be possible in a fluid, you know? So, but the fact that the plasma is collisionless allows for this kind of physics, which takes me to a very short primer of shock parameters, such that we are all on the same page. Let's now imagine that our shock is a wall, is a discontinuity, is an infinitely thin kind of system. The orientation between the normal of this wall and the upstream magnetic field is a crucial parameter. We call it theta bn, and we divide shocks into quasi-parallel and quasi-perpendicular. What happens when you encounter a large magnetic field or a wall, yeah, if we stick to this metaphor, is that you can be reflected. And if the upstream magnetic field is in this configuration, the quasi-parallel one, you can stream very far away from the shock. So at the end, you end up with the material coming to the shock and the other material going back. That creates an instability. And this very stability is the one that is giving you the waves. So basically, we are guessing that in this simulation, the upstream magnetic field is oriented that way, roughly. And yeah, that's important. Vice versa, when your upstream magnetic field is aligned with the wall, you can bounce, but then you are caught up very quickly, and you can't propagate information. This situation is happening at the flank of the structure. So this behaves like a gas. like a supersonic jet making the sonic bang or boom. Or yeah, okay. Other parameters are ratios between shock speed and local sound speed. We call it Mach numbers, and also plasma beta. That tells me in my system how much of energy basically or pressure is contained in the thermal motion of the particles, and vice versa, how much of it is contained in the magnetic field. But this is really like a primer. Let's move forward. And since I promised there was the shock part, let's have a super quick look at the particle acceleration. Two models. These are not in competition, but they are different realization of how them shocks power the most important events of particle acceleration. Yeah. In one scenario, you have a single encounter. Again, analogy of the wall. This wall is in some frame of reference moving. You launch a ball to it, and upon jumping off the wall, the ball is going to gain momentum. So that's a way to accelerate particles. We call it shock drift acceleration. Single encounter, very efficient for a few, well, we'll see that. But it predicts a very moderate energy gain. So if you go with this theory, what happens is that you routinely observe particles which have higher energies with respect to the ones that you predict. Vice versa, we can imagine now that our wall is pretty thin, and then we see the wall as or the shock, I should say, really, as an interface between two fluids like this. And so what happens is a converging mirror kind of situation. So I have at the interface between the two fluids, I have a ball that is bouncing between these two fluids, and this system gives energy, a lot of energy. It's very good to produce power law energy spectra, and it's very successful. But the trick there is that I said that we can consider the shock as infinitely thin. So that must mean that already my particles can jump very easily back and forth. This is called the injection problem. So this model doesn't really account for low energy dynamics. Right. Of course, shocks are not walls. They're not discontinuity. They're not infinitely planar. They're not time stationary. Yeah. There's many deviations from the real cases, and I want to stress that most of this knowledge comes really from in situ investigations. This is a rather busy and this is a bit of a busy slide, but I do have a few examples in which, for example, if you focus on the right, these are now we learned how to read this time series. We know that the magnetic field is going to jump up whenever a shock crosses the spacecraft, and we see that if we go there with 4 spacecraft, this jump happens at different times. So that means that the approximation by which a shock is a thin layer or a wall is an approximation which is very stringent, yeah. And this hopefully you understand this is a simulation which reproduces this behavior. So the shock is somewhere here. It's a bit like the video that we saw before, but really local. And so you see that the shock is very corrugated. I don't want to go too much into the details, but this has dramatic effects on particle dynamics. For example, the adiabatic reflection scenario in which I do the one bound, if all of a sudden my wall is curved, custom structure, I could do multiple bounds. That means more energy for me. I put this in prep paper because with Oreste we are focusing on a particular deviation from the ideal case of a wall, and we run the simulation. We run simulation to understand not only if the shock is a wall or not, but also to see different species, so different ions, if you want, in the solar wind, if they see the same wall. That's a layer of complication, if you like. We are evidence to say that different particles react differently to the presence of a shock wave. And so this effort is being done here in synergy with MMS. These are in situ mission that has very high time resolution. But so the idea here, one of the projects we're developing together is to say, okay, if we deviate from this ideal case of a shock, what does it mean for different particles? This is very poorly investigated, but has consequences in how we distribute at the end the energy. Yeah. Right. Just to be completely honest, this is for you to have a look at. A few length scales that we're going to talk about, and a few time scales. These are measured in the heliosphere. For example, an ion inertial length, or gyration of ions is going to be in this range of meters. Yeah, So these are kind of the parameters that we can access in this virtual laboratory that is the solar system. Since we have the domestic shock, the Earth's bow shock, we have that. We also observed it for a very long time. We computed these important parameters there for a very long time. And this is the kind of space that you access at the Earth's bow shock. And yeah, you have a pretty nice span, yeah? And today we're going to focus on IP shocks, interplanetary shocks. So these are the ones that are driven by the solar eruption as opposed to the obstacle in the solar wind. Why? Well, for a couple of reasons. They're basically less investigated than the bow shock, so there is interest there. But also we access a different regime because the shocks that are driven by solar eruptions are weaker with respect to the Earth's bow shock. They are larger, that's important. They don't, you know, they don't move very fast. They're not extreme systems, but they evolve. That's important. They evolve. They start from the sun and they propagate in the solar system. Whereas the Earth's bow shock is always standing in front of our planet. And so we don't really access time evolution in the system. Then there is also, but I don't want to stress you too much with instruments and stuff like that, but there is also a reason, an instrumental reason why shocks are less investigated. IP shocks, I mean interplanetary, and that's because if you put a probe there and the shock goes very fast past it, you need a very high time resolution to see the details of this event. For the Earth's bow shock, it is less important because it's always sitting there, so you can go a bit lower inside and probe it. Cool. We said the solar orbiter. Let's do a bit of solar orbiter. So far we built our knowledge from the sun. There is an eruption going off. It's gonna drive the shock. We put the spacecraft in situ. This is what a spacecraft would see. Now we are black belts of this plot. Magnetic field goes up. It's becoming our guidance to identify the shock transition. You have a spectrogram of energetic particles. This is basically in time the density of particles of high energy. So this is what you would see with a typical instrumentation of a nice spacecraft. And so you see that, okay, there is an enhancement. There is some irregularity in that enhancement, but okay, I have this continuous coverage in energy. This white stripe is just that we don't cover this energy. And the temporal resolution is what it is. It's nice, but it's what it is. So this is the amount of innovation that solar orbiter brought to that picture. This is the very same observation. This is what solar orbiter sees where other spacecraft will give you some picture like that. So there is a new data set out there, and possibility to look at very fine details of this process of particle acceleration. So all of these fine details matter because they must fit into a larger scale. At the end, I should see a spectrum of energetic particles. All right. So.
Okay, just to see the type.
What if I'm not okay?
Yeah,
I have to. I don't know.
no, it's not up to you. Okay.
It's no more time.
Yeah, proceed.
Okay. All right. So there is a new data set. We try to explore it. I mean, you can guess the title. There is a data that we try to exploit it. Yeah. That's a very quick example of how we exploited that very event. Actually, the last time I was here, I just had this observation in my laptop a couple of years ago. It was really just out. I mean, just out of the sky, you know, of the space. Sorry, I got distracted. So this is the shock wave that comes in, and so we said that we could resolve some variability. The variability I'm talking about is in this black box. So if we look very carefully at that black box, these are excited protons that come to the detector, and you see that they are not enhanced regularly, but they are enhanced in a particular way. In particular, they have a slope. So they are like stripes that are not vertical, but they are tilted. Why are they tilted? The reason is that high energy particles are faster, and so they're the first to arrive to the detector. Whereas low energy particles are slower and they arrive later to the detector. That gives you this typical slope. But then if we admit this, we are admitting that the source of these particles is somewhere far away. And we can compute where it is the source of this particle. And so this is a copy, basically, of an irregularity of the shock wave. Basically, you do some machinery, and what you come up with is a cartoon in which you probe the shock front, but these enhancements are irregular because it's an irregular shock front. And so it's producing particles irregularly. So on the right-hand side of the cartoon, you have a simulation. I don't want to go into the details of it. It's very small scale. For the first time, we could match it to the observation. And you have an irregularity indeed in your shock front, which is somewhere here. You filter and you look at the energetic particles that you can finally detect with solar orbiter, done below, and you find that indeed they are produced irregularly. So this is a way to basically get around the first problem I mentioned, the point-wise observation. So this is a way to exploit a point-wise observation to reconstruct something that is 2D, at least 2D in this case. We know it's 3D, but yeah. So I cross the shock in one point, but the context of it gives me information about the spatial structure of the shock. That's a quick example of how to exploit this data set. This is just to say that this is not only, I mean, this is going to the solar, the cycle 25 part of what I was saying. This, the fact that there is a new data set, it means that we can explore a parameter space, basically. And yeah, I mean, in this picture, you have the solar orbiter trajectory in a system where the Earth is blue and the sun is yellow, of course. This is the solar orbiter orbit. It goes very close to the sun. And the the green dots are events that we looked at in these statistics. I tried to do this exercise. I may have pushed it a little bit, maybe, yeah. So if I plot these points into the beta Mach number space, I can visualize a bit other systems. Maybe some of you are interested in these systems, and I pushed it a bit. So don't read it as out boundaries. Maybe supernova they start a bit at higher Mach numbers, or galaxy cluster is more like here. But this is just to tease you into some information that we could get to close to astrophysical systems with this sample, no? So basically here, the takeaway message of it is that we have direct observation in some parameter space, direct observation, which we hopefully is in some similar regime to systems that are only accessible remotely. We're gonna have a look at a couple of events there. So the events that you just showed, where we discovered the irregularity in proton acceleration, is the red dot. Later on in the talk, 10 minuti. All right.
15 in realtà.
All right, so, okay, cool. So later on in the talk, we are going to look at this shock, very extreme Mach number. It's going to be interesting, maybe. Let's make a quick mention then. I'm going to go a bit faster here. I discussed about solar orbiter, but of course, as I was saying, there's many other observers. So this is a bit wind is a cartoon showing these probes deployed in the heliosphere. We have Parker Solar Probe which goes very close to the sun. Bepi Colombo is gonna go inside as well, solar orbiter. So we move from a scenario in which we have a fleet of spacecraft close to Earth to a scenario in which we have many observers around. That means that not only we can do direct investigations, we can do them from multiple vantage points. That's important. I have a couple of examples of that. The fact that you saw that there was this very wonky orbit of PSP going very close to the sun, that means that we can really go and have a look at where shocks are born. This one that you see here is a map on the left. The sun is at the center. Parker Solar Probe is a NASA mission, is very close, 13 solar radii. Solar orbiter is somewhere here. And an event, so an eruption, goes off. And okay, this is nice, because first of all, we have a probe there, where this event is starting. Second of all, we have another probe to look at the evolution of the event somewhere. That's solar orbiter. So that's the observation, the in situ observation of the shock. This is very busy plot. I don't want you to really focus on it. even though now, as we said, we are black belts of time series. So you may imagine that there is some jump here. So that's where the shock is the closest ever to the sun, shock detection. And so you can do, I'm gonna go a bit fast here, but you can do, you can question basically the time stationarity and or the role of shock evolution with direct investigation. This is what the two probes I was talking about see, spaced by almost a day. So Parker Solar Probe is on the left, Solar Orbiter is on the right. I mean, even if we zoom in, this is the picture we get. Let's focus on the easiest to read the things. Is magnetic field or speed? Well, maybe let's do the magnetic field. PSP is a very sharp jump. Young shock is a very sharp jump. Solar Orbiter is a very complex jump. So that means that really these two crossings are very different. What am I saying? I'm saying that the variability in the shock system is fundamental to explain the particle acceleration. Indeed, we okay, I'm gonna skip this. Indeed, we are gonna look. People. Of course, this was a big community effort. Huh? So people looked at how the very young shock produces particles, and they found a bunch of interesting things. Namely, that they caught the process of particle acceleration in the making. The relevant representation of it is this. They call it the nose for a while. So the shock is somewhere here. Sorry, this data is not super beautiful as the one before, but nevertheless is very important. So this enhancement of energetic protons here is basically the young shock accelerating particles. Finally, this signature completely disappears at Solar Orbiter. So this kickstarting of the process was observed by PSP, and at Solar Orbiter we find a more classic picture in which the whole system it became complex, but it stabilized itself to be a steady accelerator of particles, basically. So that's one thing that you can do with two spacecraft. And there is a lot more to be done, which takes me to another project that we took in these days, which we, with Rafaela, who is here. Thanks for coming. Yeah, we're exploiting a similar kind of situation, but instead of doing a Parker Solar Probe to Solar Orbiter, we are doing Solar Orbiter as an inner heliosphere vantage point. And then we have the luxury of studying the event near Earth, where there are many spacecraft around. So that's an ongoing investigation. That's another exciting result of this visit. Yeah, nice. So back to the astrophysics question. Okay, cool. So I'll relax a bit.
Yes.
That's what about the what about electrons kind of question. I mean, electrons are relevant because when you accelerate them, they emit. I'm sure many people here know much more about that kind of stuff. So I mean, one idea could be to take that sample that we now have and basically look for accelerated electrons and repeat some of these exercises that we discussed today. And if we do that, we are in for a bad surprise because electron in situ electron acceleration to high energies is pretty elusive. It's pretty rare at IP shocks. The table, perhaps the most boring thing to put in a presentation, but this table is the outcome of several years of stereo observations. And these are the only events that basically show enhancement, well, the presence of energetic electrons of MEV. So it's just a handful, really. One of the reasons is that electron acceleration basically is works different than proton, and it's very picky about this parameter, the shock normal that we defined at the beginning. Electron acceleration, you need a really quasi-perpendicular shock configuration. And also this problem by which if you want to go in the model of diffusive shock acceleration when you bounce back and forth. To approximate the shock as thin, the electron must gyrate very large. So that means that the injection problem that we said yesterday is dramatic for them. But nevertheless, 1%, if we have 150 events, we have 1.5 events. But, okay. Sometimes we did get in situ acceleration of electrons to high energies. These are two contributions that that are out there. This is a big legacy observation. We now started to learn how to read this exponential rise of flux of energetic electrons. There is a shock somewhere here, and they caught it in the this is a smoking gun of electron acceleration. Note the energy. This is 38 kilo electron volt. Still one of the most energetic events. There is another case very recent. So during this solar cycle, again recorded by Parker Solar Probe, a very strong shock came out or went off, and somewhere there is a detection of energetic electrons. So that's another remarkable event. I think the maximum energy that they see there in situ is about 1 mega electron volt. I could be wrong, but since we had the shock list that I was just showing, the shock catalog, we went and looked for outliers, and we did find a crazy outlier. It was the point that in that scatter plot was somewhere off, no? So this was an event which crossed the solar orbiter. These are a few parameters. These Mach numbers, typically for IP shock is 1.5. So this is 28. The shock moved at 2,000 kilometers a second. Typically, they move at 500. This again is extremely good in terms of being perpendicular. So your upstream magnetic field is almost aligned to the shock front. And this is an exercise that was done. So we took the entire catalog. We normalized it so that each of these lines here is a solar orbiter shock of these 150 events I was telling you about. And so this is this event. So the black line is the event I'm going to talk about now. So this is really an outlier. The magnetic field gets compressed by a factor of 10. And I mean, this is we call it the super shock, just to make it more exciting. All right. I think I'm well on time. So this is my magnetic field, the velocity profile. You see that it jumps. This is similar to what I just showed, density or flux of energetic electrons going up. I mean, this is a first. We go to energies of up to 15 mega electron volt. So this is indeed another busy plot, but here I'm gonna spend some time discussing it. This we understand. So the last panel we skip. This panel we understand is the magnetic field. Takeaway message from here is a strong enhancement of magnetic field, and this is a very structured enhancement. So there is a lot of variability there. It's going to be important. I mean, this event must be special somehow. If it's the strongest ever recorded, it must be special. No? So we're trying to understand why it's special. Velocity goes up, okay? Density, temperature, they go up. And this is the spectrogram now of energetic electrons. And yeah, again, in time, we have the color is the density, if you like, for the flux. We have some signature that is reminiscent to what we just saw for protons in the slide before. So there is energetic particle production going on. We see that the highest energy, so these energies are spiking very close to the shock. They don't really propagate out yet. So the next question is, let's see how different particles react to the presence of such a strong shock. Also, yeah. Okay, so that's another time series. So, okay, this is how to do this. With these theories of particle acceleration, you can predict the spectrum of accelerated particles. Cool. So we can measure it. That's the measurement that we made. And this is compatible with some of the models that I was discussing before. In particular, from this, so the takeaway message from this spectrum is that probably the model in which I have the wall and the ball bouncing is being realized somewhere, but the wall is moving very fast. That's the idea. The wall is transferring a lot of momentum to the electron, at least judging from this picture, because this spectral slope you can predict. And if you admit that there is the wall and a few electrons bouncing against it, and a few other things, then you reproduce this spectrum. Okay. Again, zoom on the time series. This is the point where the magnetic field jumps. This is the the shock itself, and so we go up in energy. Each of these panels comprises of 4 plots. I want you to focus only as if they were one line, really. 4 lines. I mean, I want you to focus as if they were one line. Yeah. You see that, for example, at intermediate energies, you have this exponential rise and a plateau somewhere. But you see that your behavior changes at higher energies, and you go more towards a spike situation. Okay, that's important. That's important for a number of reasons. First of all, typically when you have this kind of enhancement, the particles are somewhat diffusing. Vice versa, when you have spikes, you have more like a situation when particles accelerated along an electric field, and that's it. So again, to this metaphor, which I'm now stuck forever, it's going to be they're at the wall, being accelerated at the wall when they spike. But there is another thing which takes me back to the importance of in situ investigation and the importance of in situ investigation at high time resolution. We see that in the legacy plots that we just saw so far, this jump was at the shock, no? The maximum jump. But now here, no, with the high time resolution, we see that the peak in these energetic particles is somewhere after the shock, like a minute or so. So that's food for thought. That tells me that the shock irregularities are playing a role such that I have a delay in the energetic particles production. And also that's remarkable, yeah. Sorry, I don't know what's going on here. So yeah, this is I'm trying to have a representation that is a bit more friendly for our eyes. In this space, there is the magnetic field, no? And the shock is somewhere here. The crazy big outlier overshoot that we saw, the magnetic field compression of a factor of 10 is somewhere here. These arrows are basically magnetic field vectors as they are probed by solar orbiter. And finally, in this plane, I plot the time series of the highest energy particles. And we see that the spike of this particle is corresponding to a rotation in magnetic field downstream. So what this tells me is, what this tells me is that, first of all, there is a smoking gun of energetic particle production in situ, which I can study. And the outcome of it, when I study it, is that the irregularity has a fundamental role. So without an irregularity, which may come from the shock or from the solar wind, I didn't have such a high energy observation. So this is to say that without this kind of complex or accounting for complexity, you don't explain particle acceleration to the highest energies. The cartoon on the right is a way to summarize. If I don't know if I'm managing to do that, but try to summarize what I'm trying to say. We divide the particles in depending on energy. This is the shock. The low energy electrons just go through. We didn't discuss them. We are not going to discuss them today. A few electrons at intermediate energy, they bounce off the shock and they do the single reflection, the single wall kind of reflection. They go upstream to do something that we'll see in a moment. And then some other people, these are some other electrons, these are the ones that give you the exponential rise. These are in some regime in which they go back and forth from the shock transition. And finally, the highest energy electrons are confined where magnetic field structure is. So this is our understanding of the event so far. since we get to such high energies, it makes sense also to basically bring together a few ideas about emissions. So this is, I don't want to go into the crazy details of this, but solar orbiter, basically we discussed magnetic fields, magnetic particles, but there are also antennas which can detect radio and a bunch of other things. Nicolina is an expert of that. And so together with the shock, we find different kinds of emission. And so this is a way, a nice way to basically join the remote sensing argument that I had before with the in situ. One exercise that we are trying to do now, so again, shock here. This spectrogram tells me basically about radio emission, yeah? These enhancements that you see here are coming from electrons that are accelerated by the shock. And so that's another way to get information about these particles. So there is another layer of investigation involved there, and this is ongoing now. So the idea again, even if we cross it with 1 point, we can use the context to address how the process of particle acceleration really works. And okay, this tells me to basically is taking me to my conclusions. The heliosphere is a unique natural lab for plasma physics. It is full of new and revolutionary observers. There is a new window to study how energy is converted to shocks, including the production of energetic particles. Hopefully, these studies they have some level of universality with the warnings of. I mean, I'm not claiming, I mean, there are warnings. For example, in my plot, say, I didn't bring a relativistic system, they don't exist notoriously. So, okay. There is a picture that is emerging where the role of shock irregularities is crucial to explain a variety of phenomena. And we got lucky that we have so many observers. And this is one of the cases where the sum of the parts is more than, I don't know how is the saying, but so basically the fact that all of it is happening at a solar peak helps a lot. So this is a gold mine to access extreme ranges of parameters that are relevant to astrophysical systems. This this was conclusion 1. Conclusion 2 is a bit of a teaser. And I tried to convince you that we could do cool stuff with 1, 2, 3, 4 spacecraft. And I want you to imagine what can be done with 7. But this is not my talk to give, it's more Federica's. So that's she's gonna give an important one soon. So that's a mission proposal to push this kind of science even further.
On April 22.
So with this, I'm gonna stop, and thanks for your attention.
Thanks a lot, Domenico, for this very nice talk. So, question in the audience or online, we have to check.
It doesn't look.
Okay, so keep an eye on that, and then if there are questions, Nicolina first.
Thanks for this great talk, Domenico. I'm impressed. I just wanted clarification for the shock that you said had a Mach number 28 observed by solar orbiter. You pointed out that the shock speed was 200 kilometers per second instead of what you call normally 500, but I was wondering where solar orbiter was, because normally in the corona, like you get as a typical value around 1,500 kilometers per second.
That's a good question. It's really, it's 2,000, no? 2,000 kilometers per second.
But where?
The heliocentric distance is of 0.6 AU. And unfortunately, it's on the other side of the sun. So we don't have other, Earth is here, the sun is there, and solar orbiter is there. So it's on the far side. Yeah.
Do you not see a type 2?
Yeah, we do. I mean, we do, and that would be the type 2, no?
Okay, so you can also compare, right?
Yeah, that would be, yeah. But it's true that this is an unusually high shock speed. Now, this is a question that we are trying to ask ourselves, because it could be two things. A, there is a patch of low pressure, so the shock goes kind of nominally. Then you find a patch of low pressure, that makes your thing go very, very fast. This is a local kind of situation. Otherwise, you have a very fast driver. So we are now trying to debate between these two scenarios. Yeah. But yeah,
No white light either, right? Because it's only solar on that side.
I have to check. There is no, so the camera, the EOI was off.
Oh,
Uh,
so it would be cool to see, like, if you can estimate even just from the CME,
yeah,
let's say at the beginning, near the sun.
yeah. Even though this is gonna be like line of sight stuff.
Yeah, but type 2 is also line of sight.
Can you get the pressure from SWA as a moment of distribution?
The pressure?
Can you get the plasma pressure from SWA as a moment of
Yeah.
distribution? So you could check this.
Yes. Yeah, there is, I made this calculation somewhere, but we don't know if that accounts for this rise in shock speed. So we missed the information about the driver as of now. We need to estimate the speed of the eruption itself.
About that nice 3D pictures with the rotation of the magnetic field, I kind of got that you think is a flux ropes kind of structure, but could also be a current sheet or some sort. So what is your thinking about that?
Yeah, we are keeping it at B rotation. It could be a flux rope indeed. It could be a current sheet. Yeah.
The large current sheet, yeah.
This is the only requirement that we have. So that is for real. I was a bit joking, but that is for real. The only requirement that we have is that in this space, this structure must be linked to the shock front. It must connect to the shock front. Otherwise, you wouldn't see the spike in energetic collector.
But as a whole, I mean, introducing the spike, no, you do not expect it. You expect that the spike is produced by the irregularities that
Yeah.
in between.
We expect that the spike is produced by the electric field inside the shock, and then it's convected along the field line. Because another idea would be if you have a Fluxor-like thing, if you compress it with adiabatic, basically compression, you can get to higher energies. But that scenario is not compatible with the electron spectrum that we observe.
Okay.
Where you have the location, would it be there a stable current sheet?
You
Stable, I mean.
mean, for example, reconnecting.
Yes.
We checked, this is also under investigation. We checked for ion jets, but unfortunately, the whole system goes very fast. And I think plasma data in this interval are at 1 second or 4 seconds. So the whole event is streaming very fast. It's,
You should go along the current sheet and see if it is filamented.
But from that plot, I see your point. But from that plot, we jump from one field line to another. So that is tough investigation. We did some stuff at high time resolution with the magnetic field and density. That we did, but we couldn't identify unambiguously ion beam. Also because an ion jet. The first reason is that the whole event is very fast, and the second reason is that the shock is very strong. That means that the downstream of the shock is crazy hot. So this distribution function are going to be very large. This is very hot plasma now. So it's tough to disentangle an ion jet in there. Yeah.
Following always the same line with simulations and which kind of simulation we have support to discriminate between these two scenarios. And on the same event, you showed the electron spectrum from different instruments and a prediction that I think the minus 2.5 was from the theory.
Yeah.
Does the theory predict also a cutoff energy, and is it possible to observe it? And could it be related to some large scale rule of thumb criterion ILAS-like to get a need and a connection with us?
Yeah, simulations, yes, but we would need a kinetic simulation. with embedded structure. This is not out of reach, but is a big effort. Is a big gap. We estimated what kind of box we needed, and this is a large box. First of all, about the spectrum, it is predicted by stochastic shock drift, so that theory, and the cutoff is also predicted by it. There is a cutoff which is compatible with this.
The green one, the green, right? Yeah.
But there is a free parameter in what kind of there is a free parameter in how energetic of a particle you can confine at the shock. So if you follow that theory's prediction, you end up with something that is like minus 2.5 and also the cutoff roughly in that area. But these are yeah. I'm not saying that this is like a one-to-one. There are error bars involved and limitation in the detection, but yeah, certainly it's not a diffusive shock acceleration like kind of spectrum.
Any other question? Because
Uh,
there's one question online.
Okay.
Yeah.
So the question, I'll read it again. Rossana De Marco is asking, thank you for the talk. Thank you. If I remember correctly, you wrote that IP shocks get old while bow shock is always young. Can you comment on that?
Yeah, that was also the question that I would like to ask to you. So yes.
So the fact that how to put this? So visually, the bow shock is always standing in front of you, whereas the IP shock depends a lot on the driver. So you're launching the shock and you make it age in the heliosphere. So this is the first visual difference. Why do we say that the bow shock is always young? It's always young because in a way is small, is a small shock. So many processes that we are discussing here rely on the fact that once you, for example, reflect a particle, it must come back to the shock. No? This configuration is hard at the Earth's bow shock because as soon as you produce the energetic particles, they're going to stream away, end up somewhere else in the path. So really, this is a question about the curvature of the system. So, so in a way, your condition upstream are always fresh. Because you never encounter before the bow shock. You
are not. I mean, there is nothing interacting there because they do not.
Yeah. Or they may come from other parts of the
Other
shock.
parts,
So you're connecting different portions. So many of these considerations don't work. Yeah. So Rostan, I don't know if I answered your question. I take it as a yes.
She always probably the weak of perhaps is saying something we are not able to.
And of course, the bow shock moves around quite a lot.
Yes.
It's standing, and the upstream solar wind is quite variable. So there's whereas the IP shock does that too, but it's second order because behind you have 1,000 kilometers a second thing that pushes.
Different. Okay. Other question? No? So no more question online. Yes, we are perfectly within the time. So thanks a lot to Domenico again.
Thank you.